Hello everyone, my name is Jinfeng, a PhD student from University of Minnesota. Today I will present my research project called HeuristicDB, a hybrid storage database system using NVM block device. At the beginning of this presentation, I will explain the background and motivations of our research. The system design and performance evaluation are discussed next. We draw a conclusion in the last section. The NVM is an emerging storage technology. It serves as either a main memory, known as NVDIMM, or persistent storage, known as NVM block device. The NVM block device has several advantages. First, compared with NetSSD, the NVM block device provides much higher read-write bandwidth. Second, compared with NVDIMM, NVM block device can be directly operated without requiring any hardware update. Considering those performance advantages, in this project, we use NVM block device as a block cache for hybrid database system. Building a hybrid storage system that using a high-performance storage device as a block cache for conventional storage usually is the most cost-efficient way to improve database system performance. Several reasons motivated us to develop a new hybrid algorithm. First, prior hybrid algorithms are built on the NetSSD and HDD architecture, which is not fit the characteristics of NVM block device. Second, without considering the characteristics of database block request, prior works have low cache hit ratio and suffers of severe performance degradation as the access pattern of a workload changed. In order to propose a proper hybrid cache algorithm, we studied the characteristics of database block request from the following two aspects, including data types and access behaviors. The data types we studied is table, index, and page. During query processing, the access pattern of each required table or index is determined and has three possibilities, as the left figure shows. And those possibilities include: first, sequential access. When no index is used for a query, the database engine scans the target table sequentially. Second, random access. When an index is provided, both index and tables are accessed randomly. Third, repeated access. When multiple operators access a table or index during a query, some pages inside that table or index are accessed repeatedly. This study aims to leverage the NVM block device as an extension of database buffer pool to boost database performance. By considering the characteristics of database block request and the performance behaviors of NVM block device, the goal is approached from the following three directions. First, guarantee reusability. In a hybrid system, a performance gain only can be delivered when a cache hit occurs. Thus, it is necessary to prioritize tables index based on their reuse possibility. Second, adaptive demotion or eviction is required. Because access patterns and required tables of each query are different, it is reasonable to adaptively adjust the priorities of database tables, index, and cached pages before running a new query. Third, the benefit of caching a page in the NVM block device. Because NVM provides much higher read-write bandwidth than conventional storage, hence, it is preferable to cache all block requests with high reuse possibilities in the NVM to deliver performance gains. Based on the design principles discussed above, a set of heuristic rules for a single query is presented in this section, and the heuristic rules for concurrent queries are provided in the later section. For Rule 1, when a table is accessed sequentially, all pages inside that table are only accessed once, thus we do not cache the pages belong to it. For Rule 2, when a table or index is randomly accessed, only a tiny portion of matched pages are accessed, and the cache pollution issues caused by omitting those pages are limited. On the contrary, those pages can deliver performance benefit once they are reused in the subsequent queries. Thus, it is preferable to admit the pages belong to that table or index. Rule 3. When multiple operators access a table or index, some pages inside that table or index will be accessed more than once. Thus, it is preferable to omit the pages from that table or index. In addition, to guarantee the pages inside the NVM buffer pool are the most profitable ones, a cache replacement happens unless its temperature is higher than the coldest one in the NVM buffer pool. For a write request, considering the unprecedented write performance of NVM block device, all write requests are buffered in the NVM buffer pool and flushed into the storage later if needed. For Rule 6, since the tables or index required and the access behaviors of each table or index varying as queries change. To admit incoming hot pages to deliver performance acceleration, a demotion or eviction of cached pages is required when a new query is submitted. An eviction action is taken if no performance benefit is provided in the past, and if there is a table or index required by both previous and newly submitted queries. Otherwise, a demotion is taken. From the storage leader's perspective, the block-level characteristics of concurrent queries are similar to the single ones. Hence, the priority assignment rules for concurrent queries is much like those used in the single query execution. More details are: when a query is submitted while one or more other queries are still running, a priority adjustment of cached pages is required. The detailed criteria are the same as in Rule 6. In addition, the access behaviors of a table or index may change after a new query is submitted. Hence, an access behavior verification is required for all tables and indexes required by concurrent queries. Finally, when multiple queries run concurrently, the quality of service for database block request follows Rules 1 to 5. To implement the proposed rules, 4 assistant programs including a query profile queue, an eviction demotion program, a table access parting detector, and page placement controller are developed. The query profile queue is developed to analyze the profiles of the past and newly submitted queries and send either an eviction or a demotion request to the system. According to Rules 6 and 7, the size of the queue equals to 2. Each item in the queue contains 2 types of variables: a table linked list, which is used to record the tables or indexes required by the corresponding query, and a performance variable, which is used to record the number of hits since a query has run. Whenever a query is submitted, its profile information is inserted into the rear of the queue. Then, the previous query's profile information is extracted. If the number of hits of previous query is 0, and there exists a table or index required by both previous and newly submitted query, an eviction request is generated. Otherwise, a demotion request is generated. To distinguish the access frequency of each cached page, a LFU data structure is used. The pages have the same access frequency and assigned into the same linked list. To perform an eviction request, we reset the access frequency of all cached pages to 0. The details are: we scan all linked lists from the lowest access frequency to the highest one in sequence, and insert every linked list into the most recently used place of the number 0 linked list. This design enables HeuristicDB to replace more easily pages that were hard in the past but are rarely accessed in the newly submitted queries. For demotion requests, the EV program performs the similar operations as for an eviction request. The only difference is it inserts all cached pages into the number 1 linked list. The table access parting detector is used to detect the access behaviors of each required table or index during query. A table is concluded to be sequentially accessed if its corresponding sequential ratio is higher than 90%. Otherwise, it is randomly accessed. Well, the sequential ratio is defined as the number of pages accessed by database reader head mechanism divided by the total number of accessed pages. To minimize the detection overhead, we only monitor the first 1% accessed pages. We conclude a table or index is repeatedly accessed if the access frequency of a page from it is greater than 1. The page placement controller is used to redirect a request into either NVM buffer pool or storage, following heuristic rules 1 to 5. When a cache miss occurs, a page placement happens only if the access behaviors of the table or index to which this page belonged is not sequential, and if the access frequency of the required page is higher than the minimum access frequency of cache pages. To evaluate the effectiveness of proposed design, a trace-based evaluation is conducted at first using TPCE and TPCH benchmark. The database size of each benchmark is set to 90 GB and 97 GB respectively. The NVM buffer pool size is set to 10 to 60 GB. 3 workloads, including a complex online analytical process workload, TPCH workload, and TPCE workload, are used for testing. We use LRU, MRU, LFU, multi-queue, arc, and TAC as baseline for comparison. Two metrics, including the cache ratio and data migration size between NVM buffer pool and storage, are employed to evaluate the effectiveness of test algorithms. From the result, HeuristicDB outperforms all tested baselines on both cache ratio and data migration size. It delivers up to 10% higher cache ratio and migrates 3.6 less data between storage and NVM buffer pool compared with the second-best algorithm. We also implemented HeuristicDB on the real system. In the experiment, MySQL runs on the top of the system. We use OptiSSD as the NVM block device, and NetSSD acts as a conventional storage device. The same workload are employed for performance evaluation. Two baseline algorithms are used for comparison, and they are LRU and the TAC algorithm. From the result, HeuristicDB delivers highest performance speedup compared with other two baselines. For instance, for complex OLAP workload, HeuristicDB improves database performance over LRU and TAC by up to 25% when the NVM buffer pool size set to 30 GB. Similar results can also be observed from TPCH and TPCE workload. We also quantify the overhead of HeuristicDB. The experimental results show that the actual memory space consumed by the HeuristicDB for storing the metadata of TPCH and TPCE is only 57 MB and 61 MB respectively. Compared with the capacities of host memory, the footprint of HeuristicDB is minimal. In addition, the actual time spent by the querying profile queue and the EV program of HeuristicDB for each query or transaction is only 0.5 to 2% of their corresponding execution time. This low overhead is because those programs are run only at the beginning of the query and are completed quickly. As a result, the computation overhead of HeuristicDB is trivial. Compared with OLTP workload, an OLAP query has higher complexity and requires many more block requests. Therefore, in most cases, the I/O time is a main bottleneck for OLAP queries. This subsection describes the detailed internals of OLAP workload. The speedup achieved by the HeuristicDB and other two baselines on each query is plotted in the figure. In the experiment, the NVM buffer pool is set to 30 GB. From the result, the HeuristicDB delivers the highest performance acceleration for almost all queries inside both the complex OLAP and the TPCH workload. The performance advantages of HeuristicDB can be attributed into two design principles. First, by considering the characteristics of database block requests, the tables and indexes required by the query are prioritized based on their usability. This enables HeuristicDB to cache the most profitable pages in the NVM buffer pool to deliver maximum performance gains with less data migration in the query execution. Second, the adaptive EV program enables HeuristicDB to evict or demote cached pages and admit new incoming hard pages more efficiently as the access pattern of a workload changed. In this work, we propose a HeuristicDB, a hybrid storage database system using NVM block device. By considering the characteristics of database block requests, HeuristicDB outperforms prior works on both cache ratio and data migration size on both OLAP and OLTP workload. Most significantly, it delivers up to 75% higher performance compared with test baselines. Here is a reference used in this presentation and the QA section, and we can discuss more if you have any questions about this project.
So thank you for the great talk. So if you have any questions, please do post on Slack, or also please raise your hand in Zoom so that you can ask the question directly here.
Yes, I'm happy to take a question now.
Yeah. So while we are waiting on questions over Slack, I have a question for you. So did you consider using NVM as a persistent memory instead of a block device, and what in your setup made NVM more suitable to be used as a block device than as NVDIM, for example?
Okay, thanks for your question. So in this example, I did not use NVM as a persistent storage. So I just directly use it as a block cache. As I mentioned earlier in this presentation, so in this project, we use the NVM block device instead of the NVM. So these two devices have some difference. So NVM is like a conventional like memory DIMM. You can directly plug in that into the memory DIMM, and it can directly communicate with the host CPU by the memory bus. But the NVM block device is kind of the block device, but the cells in that NVM block device is actually is like a 3DS point memory, a kind of the NVM.
Mm-hmm.
So that's the difference. And also the NVM block device still communicate with hosts through the PCIe interface. So that's the most significant difference. And the problem for the NVM device is it will suffer some severe performance degradation while the number of threads increase. But however, for the NVM block device, it didn't suffer this issue. So consider this performance disadvantages of NVM. So in our project, we use NVM block device instead of the NVM.
Okay. So I have one more question for you.
Mm-hmm.
So you presented many heuristic rules, right?
Yeah.
So I was wondering, like, what among those rules are specific to NVM, and like what among those rules are applicable to, let's say, any storage hierarchy, like where you have a slow device and a fast device.
Oh, so actually, those rules is only designed for the database, for the relational database. So like, yeah. So we actually characteristics the database. We studied the characteristics of database block request at first, and we found some specific characteristics of database block request, and then based on those characteristics, we designed and proposed some rules, and those rules is only applied for the database.
So let's say you have the database, right? And let's say you have the database deployed on a different hierarchy, like NAND-based SSD on top of HDDs, like where the SSD is the faster device and the HDD is the slower device. So what among those rules that you have sort of described in this paper are applicable to such a hierarchy as well?
So I think maybe if you change the storage device, for instance, you decide that in the storage, in the low performance storage device we use HDD, and the high performance storage we use SSD. Maybe our rules will not, our heuristic DB will not work well in such a hybrid architecture. This is because, for instance, the conventional NAND SSD may provide a similar sequential read performance as HDD, right?
Mm-hmm.
So that means cache the sequential read request will not give you any performance benefit. So, but in our case, we use the NVM block device as a block cache. So it provides much higher sequential read and random read performance compared with all conventional storage devices such as NAND SSD and HDD. And we prefer to cache the sequential read if that table is accessed multiple times. So it will guarantee. So in such combination, it will guarantee that we can gain some performance gains even for the sequential read request. But on the contrary, for the other combination, like you said, the NAND SSD plus HDD, our heuristic DB will not provide performance gains since the NAND SSD provides similar sequential read performance as HDD. Yeah.
Thank you for answering these questions. So if anyone else, if you have like any other questions for this talk, please post on the Slack channel. So thank you so much.